Good evening. Tonight we welcome Dr. Alex Hall, who is a Royal Society University Research Fellow and an academic staff member at the Institute for Astronomy at the University of Edinburgh. He obtained his PhD from the University of Cambridge in 2014 before moving to the Royal Observatory in Edinburgh. His research interests are in theoretical and observational cosmology, and is one of the core science leads for the Euclid mission. He specialises in cosmology, the study of the universe as a whole, and is particularly interested in the evolution of structure in the universe, from the tiny quantum fluctuations in the early universe through to the present-day galaxies and stars we see in the night sky. He's originally from the Isle of Man, which is an island in the Irish Sea, and throughout the Isle of Man's history, it's got a unique linguistic and cultural identity influenced by Gaelic and Norse cultures, and apparently it looks amazing and makes great beer. So let's give a big Mexborough and Swinton welcome to Dr. Alex Hall.
Thank you very much. Thank you very much for the nice introduction. Yes, it's a great pleasure to be able to give this talk this evening. Thanks very much for the invitation. The wind at the moment is still pretty quiet, so hopefully you can hear me all right. So I'm going to talk about this satellite. It's a space telescope. It's called Euclid. It's something that I'm spending a lot of time working on. There's a lot of people across the UK working on this, especially in Edinburgh. I'll tell you all about it and explain what the point of this thing is. Okay, first of all, I mean, you already heard a little bit of intro about myself, but I'd like to kind of just give you a bit of context about how I got to where I am now. So as you heard, I'm originally from the Isle of Man, in the middle of the British Isles there. I went to university in Cambridge and stayed on, did a PhD there in astronomy, sort of gradually specialized. I was sort of interested in lots of different sciences, specialized into physics, and I quite enjoyed sort of theoretical physics and particle physics, and that's how I got into astronomy, really. It was through that kind of interest in physics. So I stayed on, did a PhD there, and then after that PhD, I got a postdoctoral research position up in Edinburgh, and I've just stayed there been here for 10 years now. Really beautiful city, and I'm based at the Royal Observatory, which, if you've ever been to Edinburgh, it's on the top of Blackford Hill, which is just to the south of the city. Very beautiful Victorian observatory. The old building dates to 1894. So it's a great place to work, and it's very privileged to be able to do what I do. So what is it that I do? So most of my job is research. I'm funded by the Royal Society, which is the UK's national professional body for the sciences. I do have to do some teaching and some admin, unfortunately. But most of it is research. So I mean, this is the bit which I think is the most fun. So I'm going to tell you about this bit of the pie chart tonight. So as you just heard in the introduction, I'm a cosmologist. So cosmology is the study of the universe as a whole. It's the broad brush, kind of large scale behavior of the universe. In cosmology, we don't focus on individual objects or galaxies or stars. We look at the whole picture. We're trying to get a big picture of what is our universe doing? How is it behaving on average? What is its history? What happened around the Big Bang? How did we get from the Big Bang to the present day? What does the future have in store for us? And in particular, I'm interested in what makes up the universe. And this pie chart on the right of the slide here shows what we think the current universe at the present time is made of. So most of the universe is made of this stuff called dark energy. I'll explain what that is later on. About 25% is dark matter, which you may have heard of. Again, this is a mysterious kind of dark, poorly understood kind of invisible matter, and I'll say a bit more about that later as well. But 95% of the universe is dark, invisible, and not understood. It leaves only 5% for ordinary stuff. So that would be the particles that make up all the elements and the stars and the planets and the gases and the things we're familiar with, the material, the matter that we're familiar with on Earth. So this is really kind of troubling situation for cosmology and physics in general is that most of our universe today seems to be dominated by matter and energy that we don't understand. We don't have a good theoretical understanding of this at all. So, what is this stuff? So this is what is really driving most of my research, is trying to understand this more. What does my day job look like? Well, I'm quite theoretical in what I do. So I do a lot of maths, I do a lot of computing. There's me at the desk I'm currently sitting at. I have a lot of bad ideas, and they go in the waste paper basket and they're right there. But it's yeah, a lot of computing, a lot of statistics, a lot of maths. But I'm getting more kind of observational, so I'm kind of making this transition into the more kind of observational astronomy world. So this is what a day in my life looks like. Okay, let me get on to the main focus of this talk, which is to introduce the Euclid Space Telescope. So Euclid is a European Space Agency telescope. There's a picture of it on the right. I'll just give you a few facts about it. So there's another photograph. That's actually me on the left there. So I went down to see it a couple of years ago down in France. But it's an ESA mission. Technically speaking, it's a 3 meter telescope. It's sorry, 3 mirror telescope. Acts like it operates like a classic reflecting telescope. It's about 1.2 meter diameter primary mirror. There's 2 cameras on board, which I'll talk about in a bit. It stands about 4.5 meters tall, weighs about 2 tons, and the initial budget of this mission was 500 million euros when it was approved. So it seems like a lot, but it's actually not as expensive as some of the bigger telescopes like James Webb, which was many billions of dollars. So why is it called Euclid? Well, it's named after Euclid of Alexandria, who, as you may know, was an ancient Greek mathematician who was around 300 BC. And we've named it after him because he's most well known for this treatise called The Elements, which is for many thousands of years, was the standard textbook for teaching geometry. So geometry, the study of angles and the laws of straight lines and triangles and these kind of fundamental theorems that are taught even today in maths. And we've named it after Euclid because the telescope is aiming to understand the geometry of our whole universe, the four-dimensional space-time geometry, if you like. So we're sort of carrying on Euclid's work and trying to understand the shape of our whole universe. And we launched Euclid. It's been almost 20 years in the making. It's first proposed, back in 2005 or 2006 or something, and we finally got to launch the year before last now, 1st of July 2023. We had some issues with finding a rocket to put the satellite on. It was originally scheduled to be put on the European Ariane rocket launched from French Guiana. Sorry, originally scheduled to be put on the Soyuz rocket. Russia pulled out of Guyana because of the war in Ukraine. So then we were put on the Ariane queue. There was a huge queue for the Ariane rocket. It was clear that we weren't going to launch on that anytime soon. So we ended up signing a contract with SpaceX and launching on Falcon 9 from Cape Canaveral in Florida. And I'm going to show you a video of the launch. Now, there's sound with this video, so hopefully you'll hear the sound. If you don't, I think there's a button I can press to try and get it. So can we play it?
Falcon 9 has successfully lifted off from pad 40 and throttled down to prepare for max Q, which is coming up at T plus 1 minute. Power and telemetry nominal. 1 minute and about 12 seconds.
So this was a a very successful launch. It was a beautiful day in Florida, and this is very nerve-wracking watching this because this is decades of people's work, people's life, and so much effort, so much money has gone into producing this high precision scientific instrument, which is then essentially strapped to a large bomb and exploded and blasted off into space. So this was very nerve-wracking. There was a few minutes delay before it was actually confirmed that we had a communication link with the satellite, and that was one of the longest 5 minutes of my life. But eventually the signal came down and it was all fine. So I'll show you another video, which you'll see two camera shots now. One camera is mounted on the lower half of the rocket, and the other camera is mounted on the upper half, and you'll see the stage separation. You'll see the lower half falling back down to Earth. So let's just watch that.
Main engine cut off. Stage separation confirmed. MVAC ignition.
Some really cool views of MECO stage separation. And on your right-hand screen, you can see that the MVAC engine has
Both
ignited.
vehicles are following nominal trajectories.
So the lower half falls back down to Earth, and one of the reasons SpaceX was actually ended up being cheaper than the European rocket was because the lower half of the SpaceX rocket can be reused. So now we'll see the lower half falling back down to Earth, and as it falls down, there'll be another camera appear on the right that will show you footage from a small landing pad tethered in the Atlantic Ocean. So we can see what happens now.
This mission, and that is coming up here in just a few seconds, followed by the landing burn about 20 seconds after that. There you can see that the MVAC engine has shut down and the landing burn has begun on the first stage vehicle.
Lost the signal. Nominal orbit.
What an incredible.
But I think that's fantastic to see. It's an amazing piece of technology that they're able to essentially navigate a stick through the Earth's atmosphere and land it on a sixpence. So yeah, really, really cool. Okay, so after that happened, satellite Euclid was released and traveled out to a part of space called Lagrange Point 2, or L2. Now, L2 it's not a fixed point in space. It's orbiting around the sun. It orbits around with the Earth, so it's a good place to put space telescopes because the sun and the Earth are always in the same part of the sky from the point of view of the telescope. So this means you can just point your telescope away from the sun and Earth, and you never have to worry about the sun and Earth light getting in the way. It's also very thermally stable. The temperature is not varying much at this part of space, so that's really good for the instrumentation. So it took about a month to get there. It's about 1.5 million kilometers away, and let's just have a look of what's inside of the telescope. So inside we've got the mirror. So there's the 1.2 meter mirror, and it essentially works like any other reflecting telescope. So light comes in, bounces off a big mirror, bounces off several other mirrors. The light then gets split into two. So half of the light gets split into the optical wavelengths, and the other half gets split into the near infrared wavelengths. And so we have two cameras. One that's sensitive to visible light, so the light that we could see with our eyes, and the other is sensitive to near infrared light. So the visible camera, which is called VIS, this is actually built in the UK. So the UK is one of the major partners of the mission, partly because we put money into building this really cool camera. It's a very high resolution camera. It's 600 megapixels. It's got a very wide field of view, so every exposure this camera takes is about a degree on each side. So you get a very big chunk of the sky every time you take an image, but you also get very high resolution, so that you get very fine detail, and that's really important for the kind of science that we're doing, as I'll explain later. So this is actually built down at the Mullard Space Science Laboratory, which is in the Surrey Hills. It's part of University College London. The other instrument is the near-infrared spectrometer and photometer. This is built in France and Italy. Again, it's very high resolution, very high field of view, and yeah, getting that kind of near-infrared light. It's sort of difficult to take near-infrared astronomical pictures from the Earth because of the atmosphere. So getting into space is really good for getting those near-infrared wavelengths. So soon after we launched, soon after we arrived at Lagrange point 2, we started getting images down. And this sort of shows you a typical image from Euclid compared to the full moon. So as you can see, you know, every exposure we get with the camera covers a patch of sky that's actually a little bit bigger than the full moon. And for context, the Hubble Space Telescope, every exposure of one of their cameras gives you that little small square. So we're getting much bigger pictures. And Euclid is a cosmology mission. It's designed to, as I said earlier, not focus on individual things, but get the kind of broad picture. So that's why we need these big pictures, because we're going to take lots of these photographs and cover as much of the sky as we possibly can in the next few years. So this is what the raw image looks like, and we can just zoom in on this a little bit. So let's have a look at this. So this was one of the first images that we had, and it's quite raw. It's quite unprocessed. So you see strange things in here. You see weird streaks. You see little smudges, but you also see things that look like space. You see stars. You see clusters of stars. Let's have a look at this in a bit more detail. Again, you can appreciate how high resolution this one exposure is, because I've zoomed in on one of these little detectors here. But even in that, you can see there's a lot of detailed information in each of these little quadrants here. So let's have a look at this in a bit more detail. So this is just zooming in. So you see a cluster of stars on the left, and you see some galaxies. You see an edge-on galaxy in the middle, and you see this beautiful spiral galaxy on the right. So this is just really without doing very much to the images at all. So you see these streaks. These are cosmic rays. So we have these high energy particles swirling around the solar system that are striking the telescope all the time and causing these little streaks. So you see a few sort of artifacts there, but again, you see this very high quality stuff too. So what are we going to do with this thing? So as I said, we're going to take a lot of these pictures, and the aim is to map almost the entire sky that you can see beyond the Milky Way. So that amounts to about 1/3 of the sky. It'll take us about 6 years to do this. So we started the survey about a year ago almost. So it'll take another 5 or 6 years to build up this data set. And after we've done that, we'll have catalogs of, well, 1.5 billion galaxies with very high quality images. We'll also have a large sample of galaxies with accurate spectra, so we can get very accurate distance measurements for millions of galaxies. So this is going to be a huge resource for all of astronomy, and the data is all going to go public. So this is going to be, great legacy value to the research and the wider astronomy community. So this is just a little animation that shows how it's going to work. So what you're seeing here is the whole sky kind of projected in this kind of funny way, but the Milky Way is running across the center of this picture. And you also see this sort of faint band curving up from the bottom left to the top right. So that's the ecliptic plane. That's the plane of the solar system. There's dust in the plane of the solar system, and so we purposefully avoid that. So we purposefully avoid the Milky Way. But we look everywhere else. So this is sort of showing how we kind of build up area over time. So this is a huge endeavor. It's one of the largest astronomy consortia ever assembled. It's got over 2,000 members worldwide. 260 universities and laboratories represented. 17 countries represented, but mostly Europe. This is an ESA mission. It's very much a kind of Eurocentric mission. So France and Italy, the UK are the kind of main players here. But there's also involvement from Japan and from the USA and from Canada, and NASA have been involved with some of the technology as well. So this is a really big it's a really big group of people, and the UK is one of the kind of leading players in this. So we kind of co-conceived this mission, and we've had a lot of involvement with the kind of leadership teams in this mission over the years. If you're wondering where the money comes from for this, it's coming from the taxpayer because it's funded by the UK Space Agency and the UK Research and Innovation Council. So in particular, the STFC, which is the Research Council for Astronomy. So ultimately, it's coming from the government. So this is government-funded work. Okay, so that was just my kind of brief explanation of what this thing is and what it's sort of made, what's inside the technology. But what's the science here? Why have we spent 500 million of taxpayers' money on this mission? Why do we need another space telescope? Okay, what's the science? What's the point of it? So this is a mission to understand these dark components of the universe. So dark energy and dark matter. There's a few other tests we can do as well. We can test the theory of gravity. We can measure the mass of neutrinos, these little light particles. We can understand the very earliest moments of the universe. But really, we're answering these big questions about our universe. What is it made of? What are the physical laws that govern the universe on very large scales? What's the history of the universe? These big questions. And I'll explain a bit more about how we do that in a second. So the way we kind of think about this is by, first of all, thinking about how the universe has been changing with time since it was born, since the Big Bang. So, I mean, we think that about 14 billion years ago, this cataclysmic explosion happened, the Big Bang. This is a difficult diagram to kind of think about because this is showing how the universe has been expanding since the Big Bang. But it looks like you're kind of looking onto the universe from outside, but you've got to imagine that you're in the universe. So this is a difficult picture to think about. So it's important to stress that the universe is expanding, but it's not expanding into something. It's all that expansion means is that everything's getting further apart. It's like space is being stretched in every direction at every point. It's just like a sort of everything's kind of getting pulled in every direction. So this has been happening, this expansion has been happening, it's been going on since that Big Bang 14 billion years ago. But as you can see from the shape of this diagram, you see that it starts to kind of flare out. So on the right-hand side, you can see it start to kind of curve out. So what this is trying to represent is that about 7 or 8 billion years ago, the expansion began to accelerate. So prior to that, it was always expanding, but it was getting slower and slower. Gravity was kind of pulling things together and trying to oppose that expansion. But at some point, we start to see acceleration happening. And this is totally unexpected. It's not understood why this has happened. But we've invented this substance called dark energy to explain this acceleration. But it's important to know that dark energy it's not known. We don't know what it is. It's not known if it's a real substance or a real form of energy. It's really just the name we give to explain this acceleration. It's something that we add into our models to give rise to this acceleration. Dark energy, the idea's been around for a long time. I mean, Albert Einstein himself was one of the first people to propose an effect that could give rise to an accelerating universe, but he very quickly dismissed it. So it's always been around, but in the 1990s, a lot of evidence built up that really kind of cemented the idea that this is really happening, that acceleration is indeed happening. Dark energy appears to be real. And this led to the 2011 Nobel Prize for Physics. So one of the big challenges for astronomy over the last 20 years is to understand more about this stuff. Is it changing with time? How does it behave with time? How does it behave? Is it constant everywhere in space? Is there more dark energy in certain parts of space compared with others? These kinds of questions. So we have a rough understanding, but the aim with Euclid is to do 10 times better than we've ever done before and try and put some precise numbers on these questions. So you may have heard of dark matter as well, and it's these are quite distinct ideas. So dark energy, we think, doesn't clump together. We think it's more or less uniform, and it's this kind of anti-gravity force sort of driving this acceleration, pushing things apart. Dark matter, on the other hand, is more like conventional matter, except that it's invisible and is not interacting with anything. So we know that dark matter likes to clump together. And we know that in regions of the universe that are very dense, where you've got lots of galaxies, you tend to have lots of dark matter as well. We know dark matter's there. It's evidence for dark matter's been around again since I think the 1930s, but really cemented in the 1970s. It's again something that the models require to explain many different astronomical phenomena, in particular the way that stars swirl around in galaxies and the way that galaxies orbit each other in clusters, but also many other astronomical observations. So we really think that dark matter is real, and we think it's abundant. We think that it far dominates the mass in the universe compared to the normal material. So Euclid, I mean, this is a purpose-built instrument to effectively see the invisible universe, to understand dark energy, understand dark matter, and in doing so, find clues about the initial conditions of our universe. So how do we do that in practice? How do you see dark matter? I've just told you it's invisible. How would you do this? So the first thing you've got to do is look outside of the Milky Way. So we're interested in the very deep space, very distant universe. That's why we need such a powerful piece of kit. We're looking, very, very deep. So we take these very deep pictures. If you take a very deep image of space, you see pictures like this. This is a famous Hubble Space Telescope image. You see galaxies. All these little colored blobs are galaxies, each one containing billions of stars. And many of these galaxies look a bit like the Milky Way. Many of them don't look anything like the Milky Way. They just look like little smudges. Okay. Now, with these large images, you can take many of these pictures and you can start to build up a map of where these galaxies are. So I'm going to show you another picture, and this looks a little bit strange, but this is a map of galaxies. This is a real map. This is real data. Each of these colored dots represents a galaxy. Okay, so we're really thinking about very, very large scales here. Not on the scales of stars. We're kind of lumping all those stars together and asking where are the galaxies that actually house these stars? How are they distributed across space? To give you a sense of the size of this map, this is 6 billion light years across and 4.5 billion light years top to bottom. And if you look at this picture, you see some patterns emerging. Okay, it looks a bit random, but you can see it's not entirely random. There are these dark areas where you don't have any galaxies. There are brighter areas where there are more galaxies. And if you kind of like blur your eyes a bit, you can convince yourself that you can see sort of tendril-like features and you see structure here. So the idea is that what we're seeing here is the galaxies tracing out the underlying dark matter. Okay, we think that there is a dark matter structure, skeleton, if you like, called the cosmic web, or some kind of large-scale distribution of structure, and the galaxies are kind of tracing that out. It turns out to be quite an accurate way of measuring where the dark matter is. You just use the galaxies to tell you where the dark matter is. Okay, dark matter's got gravity, so it's pulling things in. So if you've got a big blob of dark matter somewhere, it's going to pull in galaxies. You'll get more gas forming, being drawn in, and you get more star formation. And so it's a fairly reliable way of learning where the dark matter is. There's another way, though, that's more direct. It's called gravitational lensing, and it's really what Euclid is a unique tool for. So let me explain this. So again, this is a Hubble Space Telescope picture, and you're seeing galaxies here. These little bright smudges are called galaxies. But if you can see on the screen, you'll see that small arc-like structures here. Okay, these are real. Okay, and what these are the images of very distant galaxies that have been distorted in a very extreme way. So what we're seeing here is a clump of galaxies, and then behind that clump of galaxies at a very great distance, much further away than this clump, we see some distant bright objects. And as the light from those distant objects travels towards us, it passes close to this clump, this cluster of galaxies. It doesn't travel in a straight line. The gravitational field of this clump is deflecting it. Okay, so it's not traveling in a straight line. And the effect of this is to distort the image of that background galaxy. It's a bit like looking at the universe through crinkled glass, where you see distortions, you see galaxies magnified or stretched out. This is a very extreme example, but this shows you the value of having a high resolution telescope such as Hubble or Euclid, where you can really get these thin features. This is a very powerful way of learning where the mass is in the universe, because it's the mass that's causing this effect. Here's another example which I quite like, but again, you can see the arc-like structures. This is a background galaxy. In some cases, you get the same background galaxy being sort of deflected multiple times. You see multiple images of the same galaxy. Okay, but you can even see, if you look at these arcs, you see kind of the features in the galaxy image itself kind of distorted out, sheared out. Another example I like to use, which I think illustrates this quite neatly, is this one. So we're looking at a swimming pool here, and on the floor of the pool we have tiles, and the tiles are laid out in a kind of regular fashion. But as you can see, as the light bounces off the floor of the pool and comes up, it gets deflected. You see refraction. There's ripples on the surface of the pool, so you can see that the regular tiles have been kind of distorted. Yeah, you also see these kind of bright features. These are caustics. This is really analogous to how gravitational lensing works. So when we look out into space at distant objects, we don't see this kind of pristine version of what's really there, because the light is getting distorted. We see these deflections. Gravity is having this deflecting effect, exactly like we see here. And there are even parts of this pool where you see, oh, there's quite strong deflections on the left-hand side there. Maybe on the right-hand side, there's a bit less deflections. You see the grid-like structure a bit more clearly. So you can almost use that to work out where is there more water in this pool. And this is how we work out where there's more mass, because we can trace out where these distortions are happening. So this is a very powerful tool, and Euclid's one of the first purpose-built telescopes to do this. Now, the way we're going to use this to learn about dark energy is by effectively looking at where the mass is in the universe, making essentially maps of the dark matter, maps of the mass in the universe out to very great distances. So we are looking back into the past, effectively, because if we're looking at those very distant objects, we're looking at the universe when it was at a much younger state, because the light has taken that long to get to us. So we're kind of looking into the history of our universe, and so we're looking back so far that we're actually seeing the epoch before this acceleration happened. So we can actually we can see what the universe looked like all the way through this phase where acceleration started to happen. So we're going to do that, and we're going to see if anything looks weird, essentially. We're going to look at how structure has been forming, how structure changed during that period, and we're going to look for any signs that structure is growing or changing in a way that's not expected. This is the way that we're going to learn about these dark components. So we'll be looking back to when the universe was about half its current age, roughly. So we're going to make a map of dark matter. So how do we do this practically? Once you've worked out where the mass is, okay, you can make some kind of map. It's a 3D map. It's a map over. You get the coordinates on the sky, but you also get that distance information, so you can make a 3D map. But how do you use that to learn about things like the expansion of the universe? So the way that we do it practically is with models. We have to make a model for what we think the universe has been doing in the last few billion years, and how mass and dark matter has been changing in that time. And our most accurate models, we have to use computer simulations to do that. So I'm going to show you another little video here. And on the left-hand side, you'll see a state-of-the-art computer simulation. This is one of the largest simulations that's ever been run. So we're looking at a big box a cubic box, and it's meant to represent a chunk of the universe on a very large scale, hundreds of millions, about 1 billion light years across almost. So, very, 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 very large scale. And we'll see the computer simulation predict how structure in the universe has been changing with time. And what this is meant to represent is the dark matter. So dark matter, it's not interacting with anything. That makes it very hard to see, but it does make it very easy to predict how it behaves because it's only interacting with itself through gravity. And we know how gravity works because we have Newtonian physics and we have Einstein's relativity. So we can actually very accurately predict how dark matter will change with time. So on the left-hand side, you'll see there are these little ripples. You can see there are little faint patches. There are brighter patches. That's where there's more dark matter. The darker spots are where there's less dark matter. On the right, you'll see a zoom in of this little area. So I'm going to set the video going and we'll see what happens. So, okay, I'm setting it running. So we start off at a very early time and we see this evolution happening and you see structure emerging. And on the right, you even see material kind of moving around. So in areas where you've got a lot of matter, these bright spots, you see material in this computer simulation falling into these dense regions just through gravity. Gravity is pulling them in. And you start to see this very complicated pattern emerge. So I'm going to play this video again, and you'll see this a bit more clearly. So let's just have another play of this. So in the early universe, we think that the universe is very smooth. There are these little fluctuations. We think those actually come from quantum fluctuations in the very early universe. But as gravity takes over, you see this very complicated structure emerge. And this actually looks quite like the map of the galaxies that I showed you earlier. So galaxies are kind of tracing out this. So the idea is that we run these simulations, and when we run these simulations, we can change things about them. We can change how fast the universe is expanding. We can change how much dark matter is there compared to ordinary matter. We can play around with the details of those initial fluctuations that evolve with under gravity. And so the idea is that we can run these, we can make these models, we can predict essentially what the matter distribution looks like today. We can make this prediction. We can say, oh, we think it has this kind of web-like shape. We go out and measure it, we compare it with our models, and that's how we learn if our models are correct. The models typically have these free parameters, these dials that we can turn. The idea is that we can turn each of these dials and we just find the combination that tells us which prediction best fits the data. So that's how we practically do this. We take our data, compare it to these kinds of models, and that's how we learn, for example, that dark energy makes up 70% of the universe today and dark matter 25%. But you can also learn a lot more. You can learn about how dark energy has been changing. If I were to put in a model where dark energy evolved with time, I would get a different pattern now, a slightly different pattern now, and at the end, a different prediction. So that's how we do this in practice. So Euclid's going to take these images of galaxies. The galaxies trace out the dark matter, and that's going to tell us how the universe has been expanding, and hence tell us something about dark energy. Okay. So in the next part, I mean, this is going to take this mission, this Euclid mission is going to, as I said, it's going to take a few years to complete. It's a very difficult mission to do. It's a very difficult measurement to make. You need a lot of information. You need a lot of galaxies. Dark matter and dark energy are very subtle effects. I mean, dark energy wasn't really discovered until about 20 years ago. So that's already telling you it's something that's quite difficult to measure. You need a lot of information, a lot of galaxies to get the precision that you need to make useful statements. So I haven't got any results on dark matter or dark energy yet. That will come in the next few years, but I do have some early images from the telescope that really just demonstrate how well it's working. So soon after we launched, we started to learn a lot about the telescope. This was one of the first images we took, and it looked absolutely awful. It looks like some kind of abstract art. This is because we had a stability issue, a pointing issue. The thing was moving around when the shutter was open. Essentially, we couldn't keep it fixed. This was actually solved after a software update, and the pointing is very stable. So some amendments were made to the software that was uploaded to the satellite 1.5 million kilometers away, and now the pointing is very stable. Another problem we've had is with ice. So there's water vapor in the satellite that froze onto some of the optical surfaces and essentially just clogged up the vision. Okay, and really had a disastrous effect on the image quality. And so what ESA did was go through this decontamination campaign where they essentially heated up the telescope a bit, essentially by just pointing it towards the sun a little bit and raising the temperature. And that worked very well. So this was a press release from March last year, just showing sort of how well this worked. So at sort of 0, 100 hours on this plot, on this diagram, they started heating up the telescope. And the blue curve just sort of shows you how the amount of light that we were collecting increased. So you see that after about an hour and a half, we were suddenly getting way more light coming in, and the ice hasn't come back. So touch wood, it won't come back. So these were the first science images released last year that really just demonstrate the power of the telescope. So this is a globular cluster. This is NGC 6397. This is one field of view, so sort of one pointing of the telescope. So you see this is a really big globular cluster. It's one of the biggest globular clusters on the sky. So these are just very dense collections of stars. They're typically very old. They've been around for many billions of years. And just for comparison, the Hubble Space Telescope, which has comparable resolution to Euclid, but much smaller field of view. So if you wanted to make an image like this with Hubble, you'd have to take lots and lots and lots of these little tiny patches. Whereas with us, with Euclid, we get one big snapshot and we get the whole thing in one go. This is another really nice one. This is the Perseus cluster of galaxies, very famous cluster. So a dense region of space where you've got lots of galaxies all clumped together. Just, I think, really nice. We're already learning a lot about the physics of these clusters, which are, there's all kind of interesting physics going on here with dark matter and hot gas, and there's a very extreme environment. Although it looks very, very beautiful in this image. And again, just to demonstrate the power of Euclid and space observations compared with ground. Here I'm showing a picture of Perseus, the Perseus cluster taken from the ground. Again, a deep image. And I'm going to overlay the Euclid image, so we'll see the improvement. So as we overlay that Euclid image, we see a lot more objects popping out because we're getting much deeper. We can see these fainter objects, smaller objects as well, because we have the higher resolution. And we got a bigger image too. So this is an improvement on many fronts. I think this is a very nice one. This is a spiral galaxy called the IC 342. It's called the hidden galaxy. It's one of the largest galaxies on the sky. And remember, the full moon is about the size of this. So this is a huge galaxy comparable in size to the full moon. This is visible, I think, from the southern hemisphere. It's quite close to the Milky Way plane. So it's actually very difficult to see. But when you go into space and you have your near-infrared camera, you can see through the Milky Way plane, and you see this fantastic image with these beautiful spiral arms. This one again, I really like. This is the Horsehead Nebula, famous nebula. Euclid's given us very, very good resolution of this. You can see the blue filamentary clouds coming off this. This is H alpha emission, and you see the magnetic field lines that are causing these kind of filaments. As I'm speaking from Scotland, I've got to push the Scottish connection to this, which is that this is actually discovery of this credited to Wilhelmina Fleming, who was born in Dundee in 1888, and she went to Harvard and was one of the Harvard people who were sort of processing the photographic plates in Harvard, and is credited with discovering this as well as many other objects. So I'm going to claim this one for Scotland. Again, I like this one. This is M78. This is another nebula, star forming, very sort of high star formation here. Huge sort of complex. I think it's in the Orion kind of star-forming region. This is an hour of Euclid observing time. Again, one field of view. So this is just demonstrating, the kinds of images we get, and with this one image, we've found about 300,000 new objects alone in this field. I'm going to show you a more recent set of images that only came out a few weeks ago, and this is European Space Agency sharing the kind of first big patch of the sky. And the patch that we're going to see is this yellow patch. So again, we're looking at a projection of the whole sky here, and we're seeing the Milky Way plane. So Euclid is mostly interested in these dark regions, kind of away from the Milky Way plane, but we've released this area which has got a bit of galactic cirrus in it, so a bit of galactic emission. So let's just zoom in on this. There it is. So this is a pretty large patch. I think it must be several, 100 square degrees, probably several hundred square degrees. You can see the galactic cirrus here, but we can zoom in on this. This is a huge image. This would occupy, many, many megabytes, hundreds of megabytes on your computer. So we can zoom in progressively. So if we zoom in, we see the top left image where you see galaxies, deep image, lots of galaxies here. We can zoom in further. That's the middle image, and now you can see, features in these galaxies. And the bottom right, zoomed in even further still, and you can see these little features. You see a barred galaxy in the bottom left there, swirly arms. You see in the center, you see a spiral galaxy. Again, great resolution there. Okay, so in sort of the final part of the talk, let me just set the stage for what's going to come in the next few years. So we make about 20 observations every day. Each one takes about an hour, and we're going to do that every day for the next 5 or 6 years. Hopefully that we can prolong the mission beyond that. The orbital insertion was very accurate, so we don't have to use too much fuel to correct the orbits or anything. So hopefully it'll go beyond that. But each observation takes about an hour. Takes about 4 hours to download the data each day. So it has to be the Earth, the ground stations that receive the data have to be in the right place. So it takes about 4 hours for this all to come down. By the end of the mission, we'll be processing a huge amount of data. As well as Euclid data, we have to use data from the ground, from ground-based observatories, which tell us, kind of give us more information about different wavelengths. So we have to process this all, and by the end of the mission, we'll be processing hundreds of petabytes of data. A petabyte, just for context, that's 1,000 terabytes. A terabyte's 1,000 gigabytes. A gigabyte is 1,000 megabytes. So this is a data set that is way too large to be handled by any single computer. And so the processing of this has to happen. It's spread out across Europe and the USA. We have multiple data centers that all take a patch of the sky, do the processing, and then it's all kind of assembled in a central location. So this is a huge data processing challenge as well. So we started full survey operations last year. This is how it works. It's pretty straightforward. We just take lots and lots of these images. Okay, we just scan the sky like this, and we build up this kind of tessellation, and we don't return. There are some patches of the sky where we do make repeat observations, and we go a bit deeper. So there are sort of well-studied parts of the sky, the deep fields, where we observe, but most of the sky is just built up in this very systematic way. Because we're doing a survey, essentially we're making a big spreadsheet, essentially, of galaxies, and each row in the spreadsheet will have some information about the galaxy. How big is it? How far away is it? What is its shape? What is its size? And we do this kind of fair and accurate, unbiased survey. So we have to kind of do this in a very systematic way. And the end goals of this are to measure dark energy at the percent level. And we want to answer questions like, is dark energy evolving? So has it been changing with time, or is it static in some sense? So this is Einstein's kind of idea right at the very start of this story, back over 100 years ago in the 20s, when he formulated general relativity. He realized that he could include in those equations an additional term that was called the cosmological constant, and that actually turns out to be a fairly accurate and fairly good model for the way the universe is accelerating. But it's not the whole story, because if that term is real, it's tempting to connect it to the vacuum of space-time itself. Particle physics predicts that there should be a term like that, a dark energy type effect, just from the 0 point energy, from the kind of fundamental energy of all the particles. But the problem is that the prediction from particle physics is way higher than what we observe. So something strange is going on with dark energy. So we want to learn more about it. I didn't talk too much about gravity, but one of the things we can do as well is test the theory of gravity, because we can run those simulations and we can make predictions for how the universe will look if gravity works in a different way. So we can, increase the strength of gravity. We can say, oh, what if gravity is a bit stronger in dense regions of the sky or something? How would that change predictions? So those are the kinds of questions that we can ask here and provide some precise answers to. I didn't talk about the neutrinos much, but neutrinos are these very mysterious particles. I mean, we know they exist. They're part of the standard model of particle physics. Until recently, we thought they had no mass, but we now know that they do have a mass. They're not moving at the speed of light. They move a bit less than the speed of light. But we don't know what precisely that mass is. In fact, we have no real clue about what the total mass is of these neutrinos. So cosmology and measurements of the large scale structure of the universe is a really good way of measuring the mass of neutrinos, because changing the mass of the neutrino affects how strong the gravity is in certain regions of space, and so it affects the sort of pattern of structure that we see. We can also try to learn something about the very early phases of the universe. Even though we don't directly measure the Big Bang, we're not looking, the very early times. We are looking at galaxies, so we're looking at sort of the more recent universe. But we can nevertheless infer something about those initial conditions. If you remember that computer simulation, that was started off at a very early time, and there were those little subtle fluctuations that evolved into the kind of large scale structure we see today. Well, you can ask questions like, were the initial conditions more complicated than that? Is that sort of smooth picture correct? By tweaking those simulations and tweaking those models, we can try to answer some of those questions too. So this is my final slide, and it's just concluding. So over the next 6 years or so, Euclid will be surveying galaxies over almost the whole sky. It's a huge collaborative effort with a lot of people in the UK, especially Edinburgh, working on this. And we're building up to a huge catalogue of galaxies, of over 1 billion galaxies, with a lot of detailed information about all of these objects. We'll use that to make a map of dark matter across the sky. And using that map, we'll make these firm statements about the nature of dark energy and fundamental physics. So this is, a very exciting time to be involved with this field. So I'll stop there, and I'll take any questions you might have. So thank you very much.
Alex, thank you very much for an absolutely terrific talk. I'm sure we're going to have lots of questions. Could I ask you to stop sharing your screen, please?
Yeah.
And we'll go back to gallery so we can see the usual suspects. As usual, ladies and gentlemen, questions and answers. If you're online, will you put up a digital hand and I'll call you in. If you're in the room, attract my attention, and we'll pull you into the discussion. So Mike Scollen's been waving at me furiously for the last 5 minutes. So in the room, Mike Scollen.
Good evening. How long after the data acquisition do you expect to be able to make these firm statements about dark energy?
So the next, there will be firm statements made in when we release our first major tranche of data, which will be in 2026. So next year, probably towards yeah, sometime next year, probably towards the end of next year. That will be a sort of represent about 2,500 square degrees of sky. So about 1/6 of the final volume of data. And then a few years after that, we'll release, I think, 3 times that, 7,500 square degrees. And then a few years after that, we'll release the full 15,000 square degrees.
Refining the statements.
Sorry?
Is that going to be refining the statements as you're going along?
Yeah. So as we, each data release, we get more data, and so we get more precision. But even the first data release will have something interesting to say.
Okay.
Tony Morris in the room.
Hi, recently there's been more interest in the MOND theories. How does that affect your work, or does it not?
Yeah, so MOND is an example of these alternative theories of gravity. And so, one of the points of this telescope is to test alternative theories of gravity. MOND is a bit different from a lot of the theories because it's mostly affecting the way that stars are moving within galaxies, and it's affecting things on quite small scales. So we can certainly make statements about MOND. We can measure, we can test ideas about MOND. I wouldn't say that Euclid is optimized to test MOND specifically, but it's something that we can test. I mean, MOND has already been subjected to quite a few tests, and the kind of simplest versions of the theory tend to be disfavored by when you throw all the data at it. But there are versions of the theory which I think are more can kind of evade some of those constraints. So yeah, absolutely, we can try and test those. Yeah.
Okay. Roy Gunson in the room.
Thanks for the talk. I've got a slight puzzle, like it's puzzled me for a long time, which I don't quite get, is the fact that dark matter has a gravitational effect on ordinary matter. It seems not to have too much effect on itself, else we would get dark matter black holes by the score because it's so much dark matter.
Yeah, no, this is a good question. So yeah, dark matter is interacting with itself via gravity as well, so it will clump together. In terms of forming black holes, I mean, we think that black holes are mostly formed from stars or from other black holes. So the conditions aren't right to have that very extreme compact environment and that kind of stellar explosion that's needed to form a black hole. I'm actually not too sure about whether it's possible to form a black hole from dark matter. I mean, it certainly is, it's theoretically possible. Whether it's sort of astrophysically possible, I'm not sure. But I mean, in principle, you could have something like that happen. Yeah,
Together.
very good question.
Yeah.
But it's certainly not how we think the vast majority of black holes are formed. Because we think that they mostly form via stars.
I mean, would dark matter fall into a black hole? I mean, that's another thing that puzzles me.
Yes, it would do. If it's a sort of massive, if it's a particle, it's got mass, it's got gravity. Yeah, it will fall in. I mean, dark matter is quite tenuous, so even though it's making up the majority of the mass in the universe, the density of dark matter is not very high, and so if you're thinking about how much dark matter is there in the vicinity of a typical star, it's not that much. So it's a very sort of tenuous kind of substance, but yeah, it would fall in. Yeah.
Okay. Thank you.
Peter Lloyd online.
Yes, thank you very much for that talk. I just had some thoughts following on what Roy's just been asking you. That if dark matter clumps on itself, it must do something similar to the formation of stars with normal matter. So, in a sense, do you form dark stars in
Well,
an earlier stage before it gets to the black hole?
yeah, I mean, it can't. So we won't get any nuclear fusion or anything like that. So the stars rely on the nuclear fusion and the energy created by that to balance the infall that gravity is driving.
Well, exactly. That's what I was thinking.
So dark matter, won't be able to produce any kind of outward pressure like that. So you won't get a stable star forming like that. You'll only get the gravity pulling it.
No, it doesn't.
Well, if it's true that dark matter doesn't interact with itself except through gravity,
Oh, I see. Right.
then that must be true.
Yeah. Okay. Thank you.
Can I just ask a question, please? So going back to your little movie on the model of the matter of the universe clumping together, and you stated that the matter clumps together through the action of gravity. Does the expanding universe have no component in that clumping? I'm thinking about soap bubbles. If you look at soap bubbles, if you've got soap bubbles in contact, you find more material at the interface of the soap bubbles. So you would expect that if you've got expanding voids of space, that at the edge of those expanding voids, the material has been piled up and pressed into those tendril-like shapes.
Yeah, that's exactly right. Yeah, I mean that's what we see. We see the voids expand just like bubbles, and you see the edges, you see voids kind of almost merging sometimes, and you see these kind of domain walls, almost these kind of structures forming along the boundaries.
My question is, what's the proportion of that effect between the expansion of space-time, and the action of gravity?
Well, the expansion of space is happening. It's the same everywhere. So we're not seeing bubbles like this bubble effect that you're talking about. It won't be happening due to the overall expansion, because the overall expansion is just affecting everything. And actually, that movie I showed, the expansion is sort of been. It's not even built into that. You've got to imagine that the whole box is sort of expanding all the time.
But you don't see space expanding like that within galaxies.
No,
you don't see space expanding like that within galaxy clusters.
that's correct. Yeah, if you've got a collapsed object like a galaxy or a galaxy cluster, it's decoupled from the expansion. The expansion is only affecting very large scales. So if you go to the scales of clusters or galaxies or smaller scales, you see no effect of the expansion. It's really something that's operating on much larger scales.
So I go back to my original point. What's the balance between the expansion of space and gravity in forming that structure, that tendril structure?
Well, the gravity is winning essentially, because you're seeing, and you see that because you see the structures grow with time. So the expansion is kind of getting slower and slower, but the gravity is winning. Now, when dark energy starts to take into effect, you see accelerating expansion, and actually, what we predict in the future is that dark energy is going to totally dominate the universe. The expansion will go off the chart, and then it will essentially win, and you won't get these structures forming, and actually it's going to smooth everything out. So far we've seen gravity winning, but in the future we'll see the large scale expansion take over.
I think I'm going to have to go into a darkened room and think about that, but thank you for the answer. Tony Morris.
When you were speaking about the Horsehead nebula, you mentioned magnetic fields. Are they taken into account in your large scale models?
They are not usually taken into account in models like the ones I showed you. Magnetic fields, they're not really affecting the growth of structure, because remember, dark matter doesn't care about magnetic fields, because from the point of view of dark matter, magnetic fields are to do with that's radiation. It's the electromagnetic field. It's nothing. The dark matter is not interacting with that. It just cares about gravity. So the dark matter will just do its own thing under gravity, as if the magnetic fields weren't there. And because the dark matter is dominating the mass, that's the most important thing. The magnetic fields can have an effect on the way that the normal matter behaves, and so we do have to think about the way those affect the early universe, where radiation was much more important, and radiation and matter was ionized, and you have free electrons, and you have a plasma. You have to worry about magnetic fields there, and you have to worry about magnetic fields in regions where you've got lots of gas, and the gas is really important, like in clusters where you have ionized gas again. And so magnetic fields are important in certain circumstances, but in terms of the very large scale structure of the universe, then they're not relevant.
Thank you, Peter. Yeah. And I think we'll make this the last question. Back to Peter Lloyd.
Oh, thank you, Paul. I'm sorry to take the last slot. It's a very simple question, actually. Is dark matter particulate?
We don't know for sure, but we suspect so. It's the leading theory. If you asked me to guess, I would say yes.
There are particles of dark matter.
Yeah, I would guess that it's a particle that we just haven't discovered yet. But there are people who think that it might not be. It might be some other explanation, but
No idea how big those particles might be.
No.
No,
we know if they are particles, we know that their mass must be at least higher than a certain number that we can measure. Because if they were any lighter than that, they would behave a bit like neutrinos, and it would mess up the models. But apart from that, we don't know much.
Okay, thank you.
Okay. Dr. Alex Hall, you've given us a lot of things to think about and to go away and contemplate. I think we'll have to return several pints of beer to make sense of the talk. Could I ask everybody to join with me and give Alex Hall a huge Reference for International Local Society? Thank you. Thank you very much, sir.
Thank you. Thanks very much.